Welcome. In this animation we derive det of a minus lambda I equals 0 for a full 3 by 3 matrix system. We start from a third-order linear ode, convert it into a 3 by 3 matrix system, and follow the exact same logical chain as the 2 by 2 case. But now we see every 3 by 3 specific detail. By the end, you will understand why every step is necessary and how the answer is built up from first principles. Step 1. We begin with a third-order linear ode with constant coefficients, introducing three state variables y1, y2, y3 as x prime, and x double prime. We can write the system as y prime equals a times y, where A is the 3 by 3 companion matrix. The top right 2 by 2 block is the identity, and the bottom row contains the negated ode coefficients. This is the same trick as the 2 by 2 case. It works for any order. Step 2. The ansatz is identical to the 2 by 2 case. Y of t equals e to the lambda t times v. The only change is that v is now a 3-component vector. Lambda is still an unknown scalar, and we are going to determine both lambda and v by substituting into the ode. Step 3. Substituting the ansatz into y prime equals ay. The left-hand side is the derivative of e to the lambda tv, which gives lambda e to the lambda tv by the chain rule. The right-hand side is a times e to the lambda tv, which equals e to the lambda ta versus because e to the lambda t is a scalar. Setting them equal gives lambda e to the lambda t versus equals e to the lambda tav. Identical algebra to the 2 by 2 case. The size of v does not matter here. Step 4. Because e to the lambda t is never 0, we divide both sides by it, and the exponential cancels entirely. We are left with a versus equals lambda v, the eigenvalue equation. For the 3 by 3 case, this means the matrix A maps the vector v in three-dimensional space to a scalar multiple of itself. The direction of v is preserved, only its length is scaled by lambda. Step 5. The same algebraic rearrangement as before. Subtract lambda versus from both sides. Insert the 3 by 3 identity matrix so we can factor, and we get a minus lambda I3, all times v, equals the 0 vector. This is a 3 by 3 homogeneous linear system in the unknown vector v. We need a non-trivial solution. That requirement drives everything next. Step 6. The heart of the derivation. Now in 3 dimensions. We need a minus lambda I3 to send some non-zero vector v to 0. Case 1. If the matrix is invertible, the only solution is versus equals 0. Useless. Case 2. If the matrix is not invertible, the null space is at least one-dimensional, meaning there exist non-zero vectors versus satisfying the equation. A 3 by 3 matrix is not invertible if and only if its determinant is 0. So we must require det of a minus lambda I3 equals 0. Same logic as 2 by 2. Same conclusion. Now in 3D. Step 7. Geometric intuition in 3 dimensions. The determinant of a 3 by 3 matrix measures how it scales 3D volume. If the determinant is non-zero, the unit cube is mapped to a parallelepiped with positive volume. The matrix is invertible. If the determinant is 0, the cube collapses. 3D space is flattened onto a 2D plane, or even a 1D line. The collapsed directions form the null space, and those vectors are exactly the eigenvectors we are looking for. Setting the determinant to 0 asks, for which lambda does a minus lambda I3 collapse 3D space? Step 8. Part 1. Before we can write down the characteristic polynomial, we need to know how to compute a 3 by 3 determinant. The Saris rule is the quickest method. Append the first two columns to the right of the matrix. Then sum the three downward diagonal products and subtract the three upward diagonal products. The three downward diagonals, AEI, BFG, and CDH, are added with a plus sign. The three upward diagonals, GEC, HFA, and IDB, are subtracted. The Saris formula is det equals AEI plus BFG plus CDH minus GEC minus HFA minus IDB. Important warning. This shortcut only works for 3x3 matrices. For larger matrices you must use cofactor expansion. Step 8. Part 2. The rigorous way to expand any determinant is cofactor expansion. Along the first row, multiply each entry by its cofactor. The determinant of the 2x2 minor after deleting that entry's row and column, times the sign given by -1 to the power of row plus column. The sign pattern for a 3x3 matrix alternates plus, minus, plus across the top row. Applying this to a minus lambda I, the first term is A11 minus lambda times its 2x2 minor. The second is minus A12 times its minor. And the third is plus A13 times its minor. Collecting all terms from the cofactor expansion. The characteristic polynomial has 4 coefficients. The cubic term has coefficient -1. Because each diagonal entry contributes minus lambda and their product is minus lambda cubed. The quadratic coefficient is the trace of A, the sum of diagonal entries. The linear coefficient is minus S2 of A, the sum of the three 2x2 principal minors. A11 A22 minus A12 A21, plus A11 A33 minus A13 A31, plus A22 A33 minus A23 A32. The constant term is the full determinant of A. This degree 3 polynomial has exactly 3 roots by the fundamental theorem of algebra, and by the Cayley-Hamilton theorem. The matrix A itself is a root of this polynomial. Let us verify this with the companion matrix for x triple prime plus 6x double prime plus 11. X prime plus 6x equals 0. Expanding a minus lambda I along the first row. The first entry is minus lambda times its 2x2 minor, which gives minus lambda times lambda squared plus 6 lambda plus 11. The second entry is -1 times its minor, a constant -6. The third entry is 0, so it vanishes. Collecting terms. Minus lambda cubed minus 6 lambda squared minus 11 lambda minus 6. This factors as minus lambda plus 1 times lambda plus 2 times lambda plus 3. The three eigenvalues are -1, -2, and -3. Exactly as expected. Step 9. The characteristic polynomial is a cubic. We can solve it by inspection, by the rational root theorem, by Cardano's formula for the general cubic, or numerically via routines like NumPy's Lena LG.eig. The three roots are the eigenvalues lambda 1, lambda 2, lambda 3. If all three are distinct, we get 3 independent eigenvectors and the general solution is a sum of 3 exponential modes. A complex conjugate pair produces oscillatory behavior. A repeated root may require generalized eigenvectors. That is covered separately. Step 10. For each eigenvalue lambda k, we find the corresponding eigenvector by forming B equals a minus lambda ki3. Then row reducing B to echelon form. When the eigenvalues are distinct, the rank of B is exactly 2, leaving one free variable. We solve B versus equals 0 and express the three-component vector V in terms of that free variable. Setting it to 1 gives us a concrete eigenvector Vk, with 3 distinct eigenvalues. The 3 eigenvectors are linearly independent and span all of 3D space. giving us a complete solution basis. Step 11. By the superposition principle, the general three-mode solution is C1e to the lambda 1 TV1 plus C2e to the lambda 2 TV2 plus C3e to the lambda 3 TV3. The original scalar solution x of t is the first component of y. To apply initial conditions at t equals 0, we set the eigenvector matrix V times the constant vector C equals the initial state y0. This is an invertible 3x3 linear system for C1. C2. C3. Invertible precisely because the three eigenvectors are linearly independent. Step 12. With three initial conditions, x0, x'0, and x'0, we form the 3x3 system Vc equals y0. V is the matrix whose columns are the three eigenvectors, and C is the vector of unknown constants. We solve for C by inverting V or by Gaussian elimination. In code, this is a single call to numpy.linalg.solve. Once we have C1, C2, C3, the solution is completely determined. Step 13. A fully worked numeric example. Consider the ode x triple prime plus 6x double prime plus 11x prime plus 6x equals 0. With x of 0 equals 1 and both derivatives 0 at 0. The companion matrix A is 3x3 with -6, -11, -6 in the bottom row. The characteristic polynomial factors as minus lambda plus 1 times lambda plus 2 times lambda plus 3, giving eigenvalues -1, -2, -3. We find the three eigenvectors, form the 3x3 system Vc equals y0, and solve for the constants. The final answer is 3/2 e to the -t minus 3e to the -2t plus 3/2 e to the -3t. All three initial conditions are satisfied. Verified. Here is the complete logical chain for the 3x3 case. We start with the matrix ode with a 3x3 coefficient matrix. We try an exponential ansatz with a 3-component eigenvector. We substitute, cancel the exponential, get A versus equals lambda V. We rearrange to a homogeneous system with the 3x3 shift matrix. We demand a non-zero vector, which forces the 3x3 determinant to 0. That gives a cubic polynomial whose three roots are the eigenvalues. Row reduction of each shifted matrix gives the three eigenvectors. Superposition builds the general three-mode solution. The initial condition system is a 3x3 matrix equation for the constants. And our worked example confirms every step. Every element of the derivation follows logically. Nothing is assumed or arbitrary. Thank you.